Okay, we're now going to have a look at doing the Launching into Space worksheet number 4, which is the next one in our series. So, looking at what we need to do, the first question on the worksheet, so this is the worksheet that you have been given, Launching into Space. So the first question is a deep space manned rocket which has a total mass of 2.1 by 10 to the 6 kilograms. So we are around about 2 million kilograms here. Is launched with a thrust of 5.4 by 10 to the 7 newtons. Okay? We are given the craft's rate of burn, which is the burn rate for the fuel, as that there as 12,200 kilograms per minute. So the first thing the sheet gets you to work through is just filling out this table. On the table here we have the time in minutes down here. So the first thing you've got to remember, or know about this table, not remember about the table, but know about it, that this is minutes here. Okay? And there is no real physics here, it's just simply mathematics. So at the moment on the launch pad we know that the mass of the rocket is 2,100,000, and after 1 minute it is used 12,200 kilograms. So this here would be the original weight minus, or mass I should say, minus 12,200 kilograms. And you have to keep on going down at time equaling 2 minutes. This would be 2440, and you can then calculate this value here. So I'm going to give you a few moments. If you just pause the video now here and complete this table, and the next slide will have some of the solutions to that. Okay, looking at some of the solutions, we've now got the masses. So I've only got here the actual mass that we need, because we don't need anything else apart from the mass. So this column here, you can check whether or not your simple calculations are working. Then we're going to use the formula that we know that we have derived in class for the acceleration of the rocket. We know that the rocket's acceleration at any time is given by this formula up here, where T is the constant upward thrust. So that's the thrust. And M is the mass of the rocket at any given time, where G is also gravity. So not going to derive that for you. So to work out acceleration, simply for the first one here, that acceleration would equal the thrust. Now the thrust was 5.4 by 10 to the 7 newtons. Now we have to assume this is a constant thrust. The design of the rocket that we are talking about here has a constant thrust from its engine, minus the mass, and the original mass is 2,100,000 times 9.8 all over the mass. Okay? So when you calculate that, you'll get 15.9, it's actually rounded 15.9 to one decimal place there, or 3 significant figures, whichever way you want to look at this value here. I'm going to give you a few moments to calculate the rest of this column going down here. I've already got the first 5 there, so you can check that you are going okay. So take a few moments now, just pause the video and calculate the values from the 2nd minute all the way to the 35th minute for us. Okay, here are the values for the acceleration. So you just check that yours matches mine. So we've got those values now. On the sheet itself, you have two graphs to create. So the first one is putting time against acceleration, and the second is g-force against acceleration. So I've just got this here so that you can check your acceleration values. But going back, we can now plot these values simply here. When we are choosing a graph, the scale has to be as large as it possibly can, and also the time, a nice spread for that as well. So let's have a look at what values should be used or is suggested here. I've got 5, 10, 15, 20, 25, 30, 35 here. So if I go up by 5 for the time here, that would be appropriate. And the acceleration values range from 15.9 all the way up to 22.5 here on this value there. Even though it only has that small range, we are not going to start at 15 on the vertical axis. We are still going to start with 0. I'll look at this in a different colour here so it stands out for just more clearly. Going up to that value again as 22. So I'm just going to go up here and make that 10, and that's 20, and that's 30. I think that's an appropriate scale. Your scales might be slightly different depending on your paper, your graph paper there. And plotting these values here, the first one is the original, or the initial is 15.9. Then it will be 16.1 after 1 minute. And so on. Let's just go to 5th minute. Now that would be 16.7, so that would be 17. Okay, and going up to the 10th minute, just getting that value from the slide, is 17.5. So the 10th minute it's 17.5. So the acceleration is not massively increasing. I think this value here is slightly out of whack. Move that one across. The 30th and the 35th minute I'll now just put in. You can do this more accurately. So the 30th is 21 and 21.3 and 35. Is 32. So it's 30th, 21.3 and 35th is 22. So we get there. Now we should notice the shape of this graph. It is not a straight line, it is actually curved. And the reason why it's curving is that the values that are creating this value, these values here for the acceleration, are changing. M is decreasing while T is remaining constant. In this case, we get a curved value. Right. The next part of the sheet or the table that we have to fill in is calculating g-force. G-force is calculated by this formula up here, and the reason why it's G plus A on the top divided by G is we want g-force is a multiple of the acceleration in terms of 9.8. So if you have no acceleration, that's zero acceleration, you are stationary on the planet surface, where A is 0, we define that as having 1g. So the formula is the gravity, 9.8, the gravitational acceleration, plus the acceleration of the rocket upward, plus, those are added together, then divided by g, gives you a multiple of g. So I want you to take a few moments to complete the g-force column. We'll just do the first one together. The first one has the acceleration, so g-force at 1 minute, at 0, would equal 9.8 plus 15.9 divided by 9.8. And when you do that, that's 2.62. As we know from the last graph that we did, the the values don't change very much. So that's just why I've gone to 2 decimal places over here. So now take a few moments to calculate the rest of that column. Okay. If you want to just check that you are going okay here, these are the values that I've calculated for the first 10 minutes. And if you want to pause there just to check, or I'm about to reveal the rest of the values. Oops, no, I'm not. Okay, so if you could do that. Once again, you just choose an appropriate scale on the bottom axis there. And here, these values go up to around about 3 and a bit in the 35th or past the 25th minute. We do realise and remember that for safety reasons, 3G, the value of 3G is set as the safety limit. So we are very close to the 3 value here. And at one stage along here, we will probably pass the 3G threshold. At that stage, we will turn the engine off and hopefully we have arrived at our orbital destination. Now, the next thing we have to do is answering the rest of the sheet, having a look at the next question. An LV is just blasting off, its vertical acceleration is that. So this is why we don't have to calculate the acceleration, it's given to us. LV just stands for launch vehicle in this case. And we have to calculate the following: the g-force of the astronaut and the mass of the astronaut, the apparent mass. As we know, the mass of the astronaut remains at 85, but because it's accelerating upward, the astronaut would feel as if he has a higher weight. So we're going to find his apparent weight. But it doesn't really change its mass at all. It's only because he is accelerating or she's accelerating. So let's start that. So the first thing we need to do is calculate the g-force, and to do that, of course, we use g-force equals g plus a g. And in this case, the 9.8 remains the same, even though as we go up higher and higher, we will only be, G will start to decrease. We are only going to use 9.8 to simplify this expression, plus 39.2 all over 9.8. And once you've got that value there, you can use we can work out the g-force. So just take a few moments to calculate that. Okay, this calculates to approximately 5g. So the value there is 5, and I'm just going to keep it as 5. And we're going to now work out the apparent weight. So the normal weight, the formula for weight, is mass times the gravitational acceleration, which is g. On the surface of the planet, this value here remains as 9.8. So when we're not accelerating, going up or moving in free fall, we experience an acceleration of 9.8, and that gives us and our muscles a certain feeling of our mass or our weight, as it's probably. So this, however, is the mass still remains as 85, but this time we are not experiencing g as 9.8. He is experiencing 5g. So it's 5 lots of 9.8. So when we calculate that value there, that will be his new apparent weight. So he would feel 5 times as heavy as he would be on the surface of the Earth, just walking around. He'd feel pinned down into his seat. This is not a safe level of acceleration, but it was accelerations that were used in the earlier spacecrafts in the 1960s and 70s. Right, we have Boris as a member of a Russian cosmonaut group, okay, and their take a few moments to read that question there. He's on his route to the International Space Station, and that's an average of altitude of 370 kilometres. We are told the original weight of the Soyuz, which is quite a small weight compared to the first example of 305 kilograms, and because it's got a small weight, we only need a small amount of thrust, and it's 4 million. Okay? We're told also the burn rate, which is 360 kilograms per second of chemical gases. That's a high level. That's before we had, the last example was kilograms per minute. This is kilograms per second. So keep that in mind when we're calculating it. And we need to calculate the G-force on Boris just after blast off. Now, to find G-force, we need, so G-force equals G plus A on G. So we need to find the acceleration. And so we go to our acceleration formula, which is T minus mg on m. So remembering this, and these are helping you through, I'm not going to calculate this for you. I want you now to place m for T, the thrust. Now here's the thrust, it's just there. And the mass of the rocket just after blast off. So this is the initial mass. So when they say just after blast off, it's at time equaling 0, really. Okay, and that would mean that the mass here would be 305,000 kilos. And G remains as 9.8. So take a few moments to calculate that value. Part B is where we are asked to find the G-force on Boris at time equaling 120 seconds. Okay? So we need to find the acceleration at time equaling 120. So just clearing all these. So our acceleration would equal T minus mg on m. Now the one thing about the formula is T does not change. It's a constant. So T remains as that value here. However, m is reducing. The reason why m is reducing is that m is being, the mass of the rocket is being spewed out the back of itself as propulsion. So the mass of the rocket has decreased quite significantly. So let's work out what is its mass. Now its original mass is 3,500 kilograms. Sorry, 305,000 kilograms as there. And we know that we are losing 1,360 kilograms per second. So that's how much loss, the change of mass would equal 1,360 times 120. So once we have that value here, which I want you to calculate, we're going to subtract them. So 305,000 minus the change in mass would give you the final mass. Now we have that value, we can place it in this formula here, and we can calculate the value of A here. Now that we have A as being discovered, we use the formula G plus A on G to discover the G-force. Okay? We expect this number here to be much larger than A. So take a few moments to calculate that now by pausing the video. We now need to calculate the value of G on the ISS, International Space Station. So to do that, we are going to use the formula for G. G is equal to capital G, capital M on r squared. So this is the gravitational acceleration from the centre of a distance from the centre of the planet, where the mass of the planet is the new top, and this is the radial distance from the centre. So we just take a moment there, and on the surface of the Earth, of course, it is 9.8. Here we are told that the mass of the Earth to three significant figures is 5.98. And the radius, now danger here is that that is in kilometres, and this radius needs to be in metres. So please don't forget to change that value there into 6,400 with 3 more zeros after it. Okay? The rest of the question now asks you to use this G that we calculate up here, this value here, and place it into this formula here, G plus A on G. Okay? And compare it then from to the value that we found in B. Okay? And what will happen is, because we are further away, this G here would be lower. And so the value actually changes. Now the last question there asks us here, this is E, why the uncorrected G-force will be used. In other words, why do we still use 9.8 in here, rather than, as this one here is a reduced value, around about 7, or a bit more than 7 there. So why do we do that? Well, humans are born on the surface of the Earth, where the gravity is 9.8, and therefore we expect 9.8. And this formula here calculates us the apparent shift of our weight in comparison to what it would be like on the surface of the Earth. So we don't care that this is our apparent weight will be changed slightly on the ISS, the International Space Station, with a different value. It's comparing it to the value on the Earth rather than the value on the ISS. If I stayed on the ISS, I grew up on the ISS, and I wanted to compare to that, then we might use the corrected value. But because we want to compare our G's to what it was like on the surface of the Earth, we will keep it as 9.8 in this formula. The next question is 5 minutes after liftoff, the launch vehicle has an acceleration of that and a mass of 125,000. We need to determine the thrust here. So this simply is a reverse of the questions. So we know the acceleration is equal to T minus mg on m. So we need to find T. We could just put the values in here and then rearrange. It's sometimes easier to do it algebraically. So ma would equal T minus mg, or T would equal ma plus mg, or simply m outside of a plus g. You don't have to do it this way. You could simply place in the values. We want to find this one here, so that's our question mark. We know the mass as 12500. We know that as 30, and we just have to rearrange. But if you do rearrange it algebraically first, before you do this, then it becomes a much simpler process. We know that the mass is 125,000, and then the acceleration is 30 plus 9.8. So you can now calculate that value. That says burn rate, by the way. It's bad spelling. The initial mass is given to you that, so we now know how many kilograms that the mass has changed. So we know the initial mass of the LV is that, and we know after 5 minutes it's that. We want to find the burn rate per second. So the change in mass would equal 290,000 minus 125,000. And once you've found that value, we want to find the change of mass per second. Now this first value here is for 5 minutes. So that is the same as 300 seconds. So dividing that value there by 300, you get the burn rate per second, the change of mass per second. Okay. I'm not going to go through the whole of this one here. This is it leads you through all of these. All we need to make sure as we go through is we're going to use the same formulas over and over again. So here we need to calculate thrust. So a manned launch vehicle has a fueled mass, so this is the initial. Its engines can generate T thrust by injecting chemical gas out from the back. Okay, we do not know its unfueled mass. Okay, and we're asked to what is the minimum thrust needed for it to lift off the ground. So we want to find the acceleration as being 0 because we want to know when our spacecraft, just ground my rocket like this, we know that it is being pulled down towards the ground by its weight as mg, but it's been pushed up by t. Okay? So at that moment, t must equal mg. So that's the minimum thrust. So in other words, this is when acceleration would just be 0. We haven't actually got it off the ground. Okay? But it's just the minimum. All we now need to do is follow the actual questions from last few questions and just adding a little bit more complexity. So what is x, the mass of the unfueled craft, if the thrust is to be 10% more than the minimum? So we are going to now take this value over here, and we know that this is the thrust that's for no movement really, but the real thrust is 10% more. Okay. So if T has to be 10% more, then the actual real thrust will be 1.1 times that value. So we just, after you've calculated this top value up here, you simply multiply it by 1.1 and you will find the real thrust. And that's the value that we can use. Okay. The unfueled craft is found when we need 2g. So we're going to use this formula as we always do. So extend this off a bit of clearance here. We know that A equals T minus mg on m. And we know that this value up here, the A, the acceleration, cannot exceed 2g. So this one here will be 2 times 9.8. This is the calculated value that we had in the last question, this part here, which is the 10% more. And the mass is what we're trying to calculate, and G, as we know, is 9.8. So you can now calculate B. Take a few moments to do that. Finally, we are asked to do the last section. The LB arrives at its orbit at an altitude of 400 kilometres. Now that's an altitude. So remember when we say altitude, we are not, altitude is how far it is away. We have to, for the radius of the orbit, we need to add the radius of the planet. So this is 400 kilometres here. And the time taken is 5.5. Calculate the burn rate. Now, from the last question, we have now the mass of the unfueled craft. So we can now calculate the change of mass as equaling 450,000 minus the value that we discovered up here. So minus that value there. Okay? Now that change happens in 5.5 minutes. So like the last question, this value here will happen over 5.5, which is 5.5 minutes equals 5.5 times 60 seconds. So we now can calculate the burn rate as kilograms per second. Now, D asks you to lead you through calculating the work required, the work done by the engines to place it in that, and that's the change. Work is defined there as the change of EP. Now, EP, as we know, is gravitational potential energy. So just get the right value up. And EP is equal to minus G mm on R. Now, to do this question, we will need to find EP in two situations. EP on the surface, and on the surface of the Earth, the following conditions are met. From a previous question, we know the mass of the Earth is 5.98 times 10 to the power of 24. We know the mass on the surface of the Earth of the actual LV is this. So that's 450,000. And we know that we are at a radius of 6,400,000 metres. So we would calculate EP on the surface with this data. We need EP in orbit, and the same thing would happen. The mass of the Earth doesn't change, it still remains as 5.98 by 10 to the 24. However, the mass of the craft has now changed, and we've calculated the mass of the craft in this question here. So we use that value. And also, R has changed. We are no longer at 6,400 kilometres radius, we're now at 6,800 kilometre radius, so that's 6,800,000. So we have been told that work is the change, and delta EP, delta equals the final condition, which is this value here, EP in orbit, minus the initial, which is this value on the surface. And once you've done that now, you can calculate the work. Take a few moments to calculate that by pausing the video. Finally, we're asked to calculate how much energy is supplied per kilogram of rocket fuel during the LV's journey into orbit. Now, to do this, we need to know how much work is done, and the work is calculated in the last question. So the energy needed to get it into orbit will be the work. Okay? We need to know the change in mass. Okay? And the change of mass would be this minus that value that we calculated there. Okay? After we've done that, then the energy supplied per kilogram would be, that's the energy per kilogram would equal the work divided by the change of mass. And that tells us, just say for instance this was 10 joules and we had a change of mass of 2, that would be 5 joules per kilo. So this is what we're asked, how many joules per kilogram do I need, okay? Or is my energy, my rocket fuel supplying for it? A very important calculation when we're dealing with getting craft into space. Okay, I hope this works. Just to make sure that all of your values, just in case for people who haven't got the access to the sheet handy, there's the table. There's the table values. Just zooming that down a bit. Sorry, too big. There's the table for question 1. Make sure. And the question in question 1 there, when would you turn it off? Somewhere between the 20th and the 25th minute would be a good time to turn the engines off. It's still too big. The answers for all the others, you can pause the video there and that will be all the answers. You can use it to correct any of your work, just seeing there's nothing else there. So. Okay. Hope everything works for you. Okay, no problem.